Hi, everybody. My name is Floyd Christopherson from Hammerspace, and I'm going to talk about Tier 0 and how that directly applies to accelerating AI workflows, not only in GPU, but primarily GPU, but any GPU or CPU-based cluster. So the problem is that, I'm sorry, I got to stay on the X. The problem is that, especially anytime you put a cluster of servers together, you need to get the data to and from the compute. Especially in a large GPU cluster, you're going over the network typically. Within each of those servers is sometimes a small amount, sometimes a large amount of local NVMe. The problem is this is stranded capacity. Even though it is extremely fast capacity, it's stranded. Data that might land on an individual GPU or CPU server, for now, we'll just talk about GPU servers. The data that might land within that server, the data that might be needed by that GPUs has to be accessed by fast external storage. Okay, a few servers, it's not such a big deal. But especially in AI workflows where context lengths are growing, where data needs to be provisioned very fast to get fast access to tokens, if every time you need to access data, you need to go over the network, that becomes a bottleneck and a problem. So you can throw network capacity at this. You can put a 400 or maybe even 800 gig network at a tremendous cost and accelerate the speed, but you're still limited by the bottleneck. Whereas within that server, you've got storage that is significantly faster than any external storage ever could be. So the challenge is, how do you actually activate that? So what Hammerspace calls Tier 0 is literally that. We aggregate all of that data into all of that capacity into one single tier of storage. But what that does now is that, and this is, again, coming back to the question earlier about how we orchestrate data, by being able to make the orchestration of that data programmatic or automated by workflows, it means that now, rather than just jumping over that extremely high performance local capacity, we actually aggregate that, and that becomes the primary storage for your workflows. Especially even in a cluster of 5 GPU servers, but especially when you get into a cluster like the example that Molly gave earlier, where you've got thousands of GPU servers, this can be petabytes of available capacity that is otherwise unused, right? And so the key here is that all of this is transparent. The automation of the workflow means that, whether it's checkpointing, if you're checkpointing and you have to wait, if you haven't upgraded to a framework that enables asynchronous checkpointing, it means that your GPUs are slowing down or stopping while you're emptying those checkpoints out of the servers onto your external storage. And I'll show you, actually results of benchmarks and performance. But that becomes a huge waste of your GPU capacity, or even being able to load much greater memory in there with existing infrastructure. At Meta, for example, all of that LLM training that they did for Llama 1, Llama 2, and Llama 3, they had a 100 gig network. They didn't put in a 400 gig or an 800 gig network. They didn't put any of that they don't need to, right? And this is the same thing that Tier 0 enables, is use the existing infrastructure that you have, but leverage the existing and, in most cases, sunk cost of this capacity within there. And let's not forget, if you're reducing the amount of expensive Tier 1 storage that you have to buy because you're able to activate Tier 0, and if you have automated orchestration that can move that data downstream to a Tier 2 or Tier 3 type storage or even cloud, it means that you're not adding power, and you're not adding cost. This is a sunk cost. Whether you're in the cloud or whether you're in an on-prem server, you've already paid for that local NVMe. So why not use it?
What's the trade-off? What's the trade-off for aggregating and taking advantage of this existing non-used storage?
Trade-off. I don't understand the question. There isn't a
So
trade-off. What you're doing is activating a resource that is otherwise not used.
Right, but if it all of a sudden starts being used, are there any other negative consequences that can happen?
Often,
Is there any?
often
Left?
people, I'll talk about some of this in the Linux portion later. Some people get concerned that, well, by using this local storage, am I going to increase the CPU load on those servers? And through testing and what we've seen in customer sites and through testing and benchmarks, the answer is no. And in particular with new enhancements to Linux, the answer is no. And in particularly for a checkpointing, that's not even a concern at all.
So you're going to show how this works?
Yeah.
Okay.
Well, I don't have a demo.
No, I don't know. No, that's not kind of show. It's just, so I have data on, tier 1, it gets loaded into NVMe of GPU server XYZ, and GPU server ABC needs that, but it's over on XYZ. It's got to get to ABC somehow.
So
the data, not the metadata. I can,
sure.
Yeah. So that's what I mean by how
well, there's two components to this. One, but they all kind of fit in with the orchestration automation that Hammerspace provides. So let's say you've got a workload and we can parallelize across all of that tier 0. But you may have an application that is using that GPU server down at the end, and the data happens to be sitting up at this end.
Yeah.
That east-west traffic is still going to be faster than north-south, but Hammerspace also has within it the ability to do what's called affinitization, which means that we'll actually place that data to the particular server that needs it, not just in the tier 0 pool.
Yeah.
So you've got already an inherent increase of speed just by the fact that it's local NVMe versus going across a network. But then you've got, through our orchestration policies, how we can intelligently place that to the correct server and in the correct place, and how much you parallelize that. And some of this also relates to what makes this possible, which is what we've put into the Linux kernel with parallel NFS.
Would it be fair to say it's accelerating the data availability and latency closer to a DAS experience and farther?
Absolutely, yeah.
Okay.
It's much more like a DAS experience, except the ability to scale that out across even massive clusters.
But so Gina, that's the trade-off. It's not an exact DAS experience,
right?
Because orchestration has to take place, but it's a lot closer to a DAS experience than if you hosted the whole thing in NAS.
That's right.
Yeah. Okay.
So what we're trying to do is, look, this is an arms race, and I'll talk about this at the end a little bit. The arms race between faster networks, which happen to be more expensive, but also faster access to the data even within the kernel. So this, as networks become faster, the kernel has to be more efficient. What we're trying to do is reduce the roadblocks and reduce the bottlenecks. And by simply activating this at this tier 0 level, that has a huge impact. And you can see it in the results. So these are, based on our testing, but let's call these theoretical results, that an 8-drive GPU server, if we assume a 90% network efficiency, that's going to be the rate you're going to get. To write 500 gigabytes, it's going to be, 4.5 seconds. Go over 100 gig up to a 400 gig network, you're going to see it goes correspondingly slower and correspondingly more expensive. If you upped that to an 800 gig network, you would be getting close, but at what cost? Especially if you have a port count that goes across hundreds, potentially, of servers. Where it gets really interesting is in the cloud. Cloud storage does not have high-performance networks. You can't get those kinds of speeds that you can get in a local network. So if you're running your jobs and your benchmark or you're checkpointing or you're running jobs that you need to be able to accessing across cloud networks, it means that your GPU efficiency, your utilization rates are going to plummet as you're waiting for data to come in and out of your external storage. By simply activating with Hammerspace, activating that local tier 0 storage, it means that you're able to do this at extremely fast levels, getting much greater utilization. We proved this at OCI in the Oracle Cloud by taking advantage of, and have benchmarks to prove it, taking advantage of inherent local NVMe that's built into those GPU servers to accelerate the performance. We also benchmarked this with MLPerf. This is MLPerf results that we just showed. This just came out, the version 2 results. And what we did is we compared, and this is certified MLPerf benchmarks that show that Hammerspace Tier 0 performs in the top ranks of other HPC parallel file systems. But what's not seen there as easily is what's seen here, and that is, what is your performance per rack unit, right? Because bear in mind, when we're talking about AI projects, it's not only Meta, it's not only the hyperscalers with mega-sized budgets. We're talking about an AI factory that may be going into an enterprise where they have to coexist with existing environment, existing IT infrastructure. And so being able to reduce the power by not having to deploy that many more, especially as you scale up and out, that many more storage servers, by being able to leverage existing networking rather than having to put a parallel high-performance network next to this and be able to do it with that level of efficiency, that's game-changing. We saw this at, and I can't name the customer, but it's a genomics research customer that has 40 petabytes of data. They've got a large cluster of GPU servers, and they were struggling. How do we actually deploy an inferencing workflow to feed those GPUs, but we spent all our budget on the GPUs. We've already got a sunk cost in the storage. How do we do this? Well, guess what? Those GPUs all have local NVMe storage. Each individual server by themselves, that storage is stranded.
This is assuming homogeneous nodes, and each one's bringing its DAS with it.
Mm-hmm.
So each one's bringing its NVMe with it. So that's why the numbers match. And
that's right.
It's I hate to say this, it's a little like linear scaling, which doesn't really exist, but yeah.
Well, and that's what we've seen. Molly referenced that earlier, even at Meta, where we scale, it is a linear scalability, and that's the power of separating the metadata path from the data path. It is a parallel file system architecture that does scale linearly. And these don't have to be homogeneous. You don't have to have just exactly the same type of server across them.
I'm just talking about the synthetic or the simulated benchmark. You're doing homogeneous servers. Yeah. Okay.
Yeah.
Mm-hmm.
Yeah. Look, that's more a matter. You're talking about this one. This is what you're referring to? Yeah. This is obviously assuming a homogeneous.
I don't know.
Yeah. This is assuming a homogeneous environment, just as we can put a placeholder. But within an MLPerf, obviously, we're building the environment itself, but it has to be, certified. It has to match this. So what makes this possible? We've talked a little bit about parallel file systems and the key here. And I'll emphasize this over and over and over again. What Hammerspace is doing is creating a standards-based environment. And the way I like to visualize that is, everything on the client side, everything that users and applications touch is standards-based. Standard NFS, standard SMB, standard S3. You never have to install a client software on your application server or change your user experience. They simply see a protocol. If they expect to see buckets, the entire global namespace looks like buckets. If they expect to see a file system hierarchy, it looks like a file system hierarchy. Where the data lives, whether it's on an object store or on high performance storage, on tier 0, is irrelevant. So part of what makes this possible is what we contributed into the Linux kernel since 2018, since actually the work began earlier than that. And this is parallel NFS v4.2 with flex files. What this does, and the vision that David Flynn and the founders of the company had was, if we can harden, PNFS 4.1 was horrible. It didn't do anything to change the problems of the efficiency problems and performance problems of standard NFS. 4.2 was designed to change that, and with flex files, and that is hardening it so it can be an HPC class parallel file system, but included in every Linux kernel, in every distribution, in every data center. That means getting rid of the NFS, the get-atter chattiness that is just bedevils any NFS traffic. It means adding the telemetry feedback. So the client, which is already in every data center, the client knows if you've got a slow performer over here or a network blockage over there and can adapt to that. Standard NFS, it chokes and fails, and that doesn't help you. And then added NConnect and much more. By separating the data path from the metadata path, you get that, as close as you can get to linear scalability because the data is just direct. But also, let's keep it standards based on the server side. So standards based on the front, meaning anything looks on the back, all you need is NFS v3. And that is where, the enhancements to KNFSD and what is in the actual server side means that I don't have to have some exotic client. I don't have to deploy a special type of server. I can take any storage server that is going to have NFS. It'll always have NFS v3. And you simply plug it in and it's available. At Meta, that's exactly what we did. 1,000 storage servers. They were all running standard Linux. They all have KNFSD, NFS v3, and we simply plugged in our metadata servers, and we could see all of those and map that directly to 24,000 GPUs. And we didn't have to install anything on the client side, didn't have to install anything on the server side. So Hammerspace keeps its magic in the middle. And I'll talk a little bit more about that. Yeah.
This is why we don't have to load anything on the GPU servers.
Yeah,
I think that's important.
So Gina, you'd asked, trade-offs and so forth. The focus on standards means that you don't have to add anything to those GPU servers. We don't have to install anything in the client. We don't have to install anything on the servers. Everything that is already in those servers is everything you need to do it. All you need is a Hammerspace that can actually orchestrate the data and unify that capacity across the servers.
Okay, I just still have questions about that because just fundamentally, I don't believe there's no trade-offs. There's always a trade-off for a technology choice, always. And I can remember back in the day, I did backups for a good part of my career when everybody wanted to go to agentless. If you did not use an agent, you could not get a granular backup RTO. So that you needed an agent to get that, and that was especially important when people were still managing things like Exchange online.
Sure.
So okay, if you're saying there's no trade-off, I'm really comfortable with that. But there's got to be things that you will not be able to do if you give it up. And I'm just not saying this is actually great. I think it's really awesome. But what I would like to know what the trade-off would be.
Well, maybe look at it this way. It takes a lot less heavy lifting if we were to create our own kernel, as many of our competitors do, our own version of the Linux kernel, and require a customer to install that version, that proprietary version, like installing an agent or like installing other sort of things on the client side. That's a lot easier path. If I were to go to an investor 15 years ago and say, here's my grand idea. I'm going to spend 8 years developing and putting into the Linux kernel all the stuff that I could do in 1 year if I kept it proprietary, and going through all the process of validating that through IETF and up into the Linux community. They'd say, you're crazy. Why not just do it and then install it in the customer side? Well, the vision was, if we can democratize that front end so that it actually, without having to sacrifice. It takes a lot of heavy lifting. We've got over 3,000 enhancements to the Linux kernel over the last 8 years that have done this. But we've contributed those into the community so that from a customer standpoint, they don't have to install anything. It's already installed. but the heavy lifting is still there. And, but we've just done it in such a way that it already exists within every data center on the planet.
I hear you.
So the way this works is, and again, this is very, is that because now the metadata servers are connecting to all of those servers above, and we've got our standard connection down to the bottom, it means that now this is all part of the same namespace. It's just Linux on the front, and it's just Linux on the back. And Hammerspace sits on the side with our metadata servers and is able to assimilate that, orchestrate that, and initiate the data movement. What that means is now that any volume that's created in the GPU servers or on the storage side simply becomes part of the Hammerspace global namespace, and which is abstracted behind our parallel global file system. Any protocol out the front sees any data on any storage, including tier 0 on the back. It's all one unified data plane.
So does Hammerspace have the capability to present any of those protocols natively,
Yes.
like outbound? Okay.
Yes.
Okay.
Yeah. So if
Not just NFS.
No, not just NFS at all. No, we have a lot of customers with applications that expect to see an S3, and well, guess what? That data might be sitting on a local NVMe that is accessed through, or onto a storage server that is accessed through NFS, but to them, they see an S3 bucket, not a copy put into an S3 store and presenting that S3, but it's the same, it's on whatever store.
Right.
And that data, part of the beauty of PNFS 4.2 is when Molly was talking about moving the data from here to there non-disruptively, well, that's live, what's called live data mobility. That's part of the underlying structure, which means because the metadata layer is unified, I can be moving that data behind the scenes and users wouldn't even know. You could have a live file open, reading and writing on that file, and I can be moving it from one store to another, and the user wouldn't know.
Let me ask a feels like a dumb question, but Hammerspace, wherever hosted, acts more or less as an acts as a client to all these protocols. So that when you talk about creating a volume, just like any client might, I don't know how, there's lots of ways to do it. The client can, by doing the appropriate query, finds the volume, and then you go through this, slurping up of all the metadata on the volume. Similarly with destruction, it's. So the tier 0 element to this is to access the NVMe on each GPU server as if it were a storage node.
Just looks
Same
like
thing.
a storage node, yeah.
Okay. So,
But normally, normally those pathways are internal. But you're saying with no agent and no installed software, you're able to. So how do you do that?
Because we've put the agent into the Linux kernel, and it just happens to be part of the standard.
So there is an agent. It's just integral to the
just
Linux
already
kernel. So there's no special trick to it.
No.
Like there normally would.
Well, the special trick, the secret sauce that makes this work is you got to be able to orchestrate the data. Anybody.
No, I mean to flip that, not flip it really, but to enable the what is a compute node to also appear as a storage server.
I mean,
for the purposes of Hammerspace.
That's right. And hyperconverged systems do that today, but each server is an island. And so what we're doing using parallel NFS is stitching all of those together into a shared pool, right? And then with our orchestration, making that transparent so it can go upstream and downstream, north-south, but it's the east-west binding it together as a shared pool that is where PNFS helps with that.
Yeah, and this is a really useful service, but as you know, if I'm getting down to sort of the root of where this differentiation comes from, maybe, or the value point here for Hammerspace, and I'd like to thank Ray for helping to point this out in a separate conversation. It's that incorporation into the Linux kernel, so that there is sort of this, provisioning free.
Yeah.
You provision Linux and you're provisioning Hammerspace.
Yeah.
Provisioning free element of it.
That's right.
And as Molly pointed out earlier, you have one of the NFS folks, and I think someone else.
We've got 2 Linux kernel maintainers.
Maintainers, on staff at Hammerspace.
I'm going to jump ahead a little bit because I want to.
have a question, but
Yeah.
can you go back for just a second?
Yeah.
Because you're showing this as Hammerspace consuming like an NFS3 on the Linux boxes.
Mhm.
Is there any reason why it couldn't consume EXTFS?
Yeah, anything, but it's typically NFS v3 is what we'll see, but we don't really care on the
Okay,
back
but
end.
it could be a local file
Yeah.
system rather than a network file system.
Yeah, I mean, it depends really on the use case, and especially in a parallel NFS environment, we would typically want KNFSD on the back end, but it doesn't really matter.
Okay.
We're going to run out of time here, so I want to give Kurt a moment, but I do want to talk about other things that we've put into the Linux kernel. And this also helps to, I think, Gina's question earlier about potential downsides on that CPU utilization. So within the Linux kernel, the way that the NFS data path was constructed, it always assumed that you were going to external storage. We recently added, and this went into the 6.12 kernel last November and was now in RHEL 10 in May. What we've done is we call a local I/O, which is basically, it's adding intelligence into the client that says, oh, this data storage that I'm accessing is on the same host, it's local. I don't actually need to go through the network stack. So where this really benefits is that it reduces CPU utilization and it dramatically accelerates write performance. And so some of the ML perf numbers that you saw before took advantage of this. And it's in the standard kernel, so it enables us. And this is part of a legacy of what we've done. We don't have time to go into all of these, but from the left going back to 2017, 2018, up through what's now coming out, striped flex files and uncached I/O improvements. I will, in another time, go into much more detail on these. But all of these things are contributions that we've put into the Linux kernel so that standard Linux, and especially NFS, the parallel NFS, and all of the related to the parallel file system, gets HPC class performance that kind of gets back to the holy grail that Los Alamos wants of being able to eliminate luster, eliminate this profusion of parallel file systems. The last in that on the far right, which is upcoming, the last 2, end clients to one file. This is the classic mod sim, many to one type of workflow that PNFS is not good at today. We're really good at many to many, but the holy grail is being able to do the many writers, thousands of nodes writing to a single ginormous file, which is what you'd get in classic HPC environments. So this is a continual investment that Hammerspace is making into the standard. Why? So that the clients don't have to ever install anything. And this is a lot of work. And it's a lot more expensive than just simply putting a proprietary client out there. But this is the history of what we're doing, and you'll continue to see this.